Hello everyone. In this session, we are going to see battery management system functionality. Okay, now we are going to see the BMS functionality overview. Okay, now we move to the battery management system functionality. A modern BMS does much more than the measuring voltage and current. Okay, it performs three major functions. First, controlling charging strategy. Second, managing the thermal conditions. Third, controlling the operational states through structured logic. Okay, all of this is done to ensure safety, optimize the performance, and maximize the battery life. Okay, now we are going to see the charging strategies used, where the BMS must carefully decide how the battery should be charged. Okay, charging too fast improves availability but may reduce the battery life. Charging too slowly improves the longevity but reduce system performance. Therefore, charging strategy is balance between charging speed, battery life, energy efficiency, and safe charging termination. Okay, the most important requirement is preventing overcharge, as even mild repeated overcharge can create dangerous condition in lithium-ion batteries. Okay, now we'll know that mostly used charging method is CCCV, where here CCCV charging method, the constant current and constant voltage method is the most widely known charging strategy. Okay, in the constant current phase, the battery is charged at the fixed current. During this phase, voltage gradually increases. Once the maximum voltage is reached, the system switches to the constant voltage mode. Okay, in the constant voltage mode, the current gradually decreases as the battery approaches full charge. Fine. The charging terminates when the current falls below a predefined threshold. Here you can see the figure. In this graph, we see the current remaining constant during the first phase. Okay, voltage increases steadily. Then during the constant voltage phase, voltage remains fixed while the current tapers down. Okay, this works well for a single cell. However, in a large battery packs, we cannot control individual cells. Okay, where cells may have different state of charge. Some cells may reach cutoff voltage earlier than the others. Okay, this create a risk of overcharge in weaker cells. Therefore, CCCV cannot be directly applied to large format battery packs without the modification. For that, we are going to use target voltage and constant current methods. Okay, because CCCV have the limitation in large packs, alternative strategies must be used. Okay, here in target voltage method, an initial voltage slightly below the final CV voltage is selected. Okay, where the battery pack is charged at maximum allowable current. When the highest cell reaches the target voltage, current is reduced. Okay, then the target voltage is increased gradually. Okay, the target voltage approaches the final CV value. Then this prevents the sudden voltage overshoot and reduces the overcharge risk. Okay, then coming to this constant current method, in systems without precise current control, a constant current charging may be used. Okay, a target voltage is already defined. Fine. When the highest cell reaches this voltage, charging will stop. Fine. The battery is allowed to relax. When the voltage drops below the restart threshold, then again the charging resumes. Okay. Near full SOC, charging occurs in pulses. Okay, relaxation periods increases as the battery approaches to the full charge. Okay, here we can see the graph. Okay, these graph illustrates target voltage charging, constant current charging. We can notice how the current pulses shorten the relaxation period, increases as full charge approaches. Okay, these strategies approximate CCCV safely in large battery packs. Okay, now we're going to move into the thermal management, where in a large format battery system, thermal management is critical, where the battery temperature affects performance, aging, and the safety. So the BMS monitors battery temperature continuously. Okay, it may also monitor coolant inlet and outlet temperature. Okay, for that, the BMS controls fan, pumps, valves, heaters, or chillers. Okay, feedback from these devices ensures they operate correctly. Okay, where the thermal runaway prevention is a key responsibility. Okay, now when the battery is heating, when the battery is heating, multiple safety layers must be implemented. Okay, single point failures such as welded contactors must not cause uncontrolled heating. Okay, redundant protection is essential to prevent catastrophic events. Okay, now we're going to see the operational modes. Now here you can see that the modern BMS uses finite state machine to control the operation. This means the system transition between defined states based on external commands, internal battery conditions, and detect the faults. This structured control ensures safe operation and predictable behavior. Okay, now let us understand the main states. Okay, now sleep mode. In sleep mode, contactors are open. Okay, battery is disconnected from the load. Power consumption is minimized. Okay, monitoring circuits are mostly inactive. This is used when the system is turned off, such as in electric vehicle parked with the ignition off. Okay, now coming to the idle mode. In idle mode, contactors are still open. However, monitoring circuits are active. Voltage, temperature, and SOC are updated. Fault detection is running. Communication buses are active. This ensures the battery is safe before the connection. Okay, now coming to pre-charge mode. In pre-charge mode, the high voltage bus is gradually energized. Okay, this prevents large interest current. If pre-charge is successful, contactors close. Okay, if fault detected, the system moves to the error state. Okay, then coming to the online mode. In online mode, the battery is connected. Charging and discharging are allowed. Monitoring continuously happening. Power limits are calculated dynamically. Okay, now coming to the error mode. In error mode, contactors are open. Charging and discharging are avoided. The fault codes can be retrieved. Okay, the system must avoid endless cycling between error and active states. Okay, now coming to the preconditioning and state transition. In some cases, the battery temperature may be outside the safe operating range. Okay, in preconditioning mode, the thermal management adjusts the battery temperature before allowing the operation. Okay, contactors are remain open. Only when temperature is within the safe limit does the system move to the online state. Okay, here you can see the state transition diagram. Okay, this diagram shows the transition between sleep, idle, pre-charge, online error state. Okay, here you can see the transition is happening between sleep, idle, pre-charge, online, and error states. Okay, the BMS is continuously evaluate the system condition and moves between the state safely. This structure which will control the state is critical for safe large format battery operation. Okay, now the battery management system functionality extend far beyond the measurement. Okay, it intelligently controls charging strategies. It manages thermal condition to prevent the unsafe situations, and it uses structured operational states to ensure the safe transition. Okay, a well designed BMS integrates accurate sensing, intelligent charging control, robust thermal management, and disciplined state machine logic. Okay, together these ensure safety, longevity, and optimal performance of the modern battery system. Next lecture will discuss the charge balancing and SOC. Thank you.